I'll show you.
You're going to give us projection.
No. I think I told you that on the quiz day. I gave it to you then, but I said you would have to know it by the test, yeah. So every formula from 13.3, all those specific formulas about the TNB reference frame, I'm going to give you those. And on one level, 13.3 and 13.4 are very similar. They're both real-life applications of all the math that we have done so far. So 13.3 is a problem, if you do it all the way out, it's just like all the math we've done comes up in the middle of it, yes? So it's just one of those situations where if you go into aerospace engineering, space, craft, trajectory, whatever, you're going to live TNB. You're not going to necessarily be doing the calculations, but you have to understand what goes into them so when you read the program, whatever it says, you know what it means. So you're going to be living in those reference frames, yes? Because you could have like structural stress on your spacecraft. If it exceeds a certain amount, your spacecraft's going to break apart. So the length of the vectors pointing in certain directions could tell you, hey, the structural stress in this direction is too much. If you want to turn that way, we'll try it, but your spacecraft might break up. And you got a nice little spacecraft here. I don't want that to happen. You guys kind of with me? So it's anyway, in terms of our class is not aerospace engineering, last time we checked. Our class is not space flight trajectories, as far as I last checked. It's math. 13.3 is all about the math. There's a lot of math. It's good math. So if there's nothing specific anybody wants to start with, I'm going to start with this little handout, practice from 13.3. Okay, let's do that. So let me give you this. All right, let's see. Let's take a look here. Now, on the actual test, depending on the kind of function I give you, I might give you more. But for example, I would give you at least all of these, yes? You with me? So then it would just be up to you to be able to do the math that this asks for, yes? Okay. Let's see. Oh yeah, I'll do that at the end. I can actually graph this thing for you at the end and show you the TNB reference frame that we're calculating. But let's try this out. Oh, come here. I might as well take you out. Come here. All right. 1A. What's that? How do you do that? That's right, just take the derivative. So go ahead and do that. I think I remember this working out. I haven't done this since I made this worksheet, which is about 6 years ago. But I'm pretty sure I remember this works out pretty nice. We'll find out together. All right, these poor little things. All right, let's see. So if I take the derivative of each component, 4t, what do I get here? This is interesting. Some nifty stuff happens.
2
Yeah, I get cosine t. Well, okay. So I would do derivative of the first times the second. Right? Because what do I have to do here? Product rule, yes. So sine t goes to cosine. Derivative of t is 1 times cosine. Minus t, derivative of cosine is negative sine. Okay, let me stop for a minute. Is everybody with me? So that kind of question should be bread and butter. That should be, give me a ton of those, Jeff. Dear God, yes. Right? I could do product rule in my sleep, no problem. Or at least in a dazed state. What about this last dude?
Sine t
Sine t
plus t cosine. T plus t cosine.
So this would be negative sine t, right? Plus sine t. Plus t cosine t. And this, of course, would be the good old product rule, yes? So everybody with me? You sure? Okay. Do you see anything good happening? I'm probably gonna ignore, I'm gonna do these problems, but I'm gonna need more room and so are you. So we're just gonna kind of do the problems as we can, where we can. So I'm gonna put over here, what is r prime if I kind of simplify this? 4t, t sine t, t cosine t. Okay, so it's already better than it looked like it might be. Let me stop for a minute. So that's not too bad. What does that point in the direction of?
Normal to the spacecraft?
It's actually the exact opposite. It's the tangential to the spaceship. Because if I divide that by its length, I'll get the unit tangent vector. Yes? So that points in the direction of where the spacecraft is headed. And of course, when I say where the spacecraft is headed, there's 3 directions that it's trying to keep track of. Yes? Okay, I like it. Hey, Mikey. All right, and then now that I've got r prime, I can immediately get the length of the arc from t equals 0 to t equals 4 by doing that. What do those symbols mean inside that interval? No. Length, yeah. So what is the length of r prime? Yeah, so this will be the square root of 16t squared. Yes? Plus
T squared sine squared.
t squared sine squared. Plus
T squared cosine squared.
t squared cosine squared. Let me stop for a minute. Is everybody with me? Because of course that's just the distance formula, right? Because we assume r of t to be starting at the origin, same thing with r prime. So then that equals, what's t squared sine squared plus t squared cosine squared? T squared plus 16t squared is 17t squared, which is t rad 17, because we know that time is positive in this problem. Time does not have to be positive, but in this problem it is. Time does not have to go forward, but in general it does in terms of our observations. You guys okay? You guys, I'm sorry. Let me stop for a minute. This, do you remember from that glorious time, last time we met? And I was just up here like spewing math at you. It was kind of silly. Do you remember there were some other formulations I gave you, like r prime cross r double prime? There were some other formulations in terms of r to calculate some of this later stuff. Depending on the, let me take it here. Depending on the function I decide to give you on the test, I might give you another formulation, but I'll give you the formula. You don't have to memorize any of the NTB stuff. TNB, however you say it. Okay. Let me stop for a minute. Is everybody with me? You just have to know how to do the mathematics. That's all you have to know. Okay. All right. That is better than we thought it would be. Yes? Compared to what we started with. So now to figure out the length, I just have to integrate from what to what? Holy shit. And then we figured out it's t rad 17. Yes? Rad 17 is just a
Number.
constant, so who cares? What's the integral of t?
T squared divided by 2.
Yeah, so this would be this from 0 to 4. So I end up with 8 rad 17. You guys see that?
Yeah.
4 squared 16 divided by 2 is 8. So I get 8 rad 17 units, whatever the units are. So if I were to plot this arc, and I will later in Desmos, we'll plot the arc, it would be that long of an arc from t equals 0 to t equals 4. And that's a difficult thing in general to do. The reason that this could get really disgusting is because this thing is moving in all 3 directions. So to get the total length, you should expect it to be generally gross. This function, this space curve, looks gross, but once we graph it, you'll see it's not that bad. That's why things simplify down so well. So obviously, if I give you a problem like this on the test, I'm going to give you a function where things should simplify down pretty well. Can you imagine? It would be very easy to do everything we just did and end up with this being absolutely disgusting.
Yeah.
I mean, like, really disgusting. So I'm going to be careful because at that point, it's just busy work if I do that to you in a test. Yes? And I try to avoid that.
So if it looks like it's going off haywire, we should assume.
Double check the work prior. Yes.
Okay, cool.
Yes. Sometimes what I'll do, especially with something where I can see that somebody makes symbols, but I might say verify that T of T is this, just so you know what your goal is. And if you can't get there, you can at least do the rest of it using what I said it should be. Yes? Okay. Now, I didn't miss anything yet. How do I get T of T?
You take r prime divided by.
Yeah, so we got r prime, and we got the length of r prime. So take a minute, go ahead and put that together. Oh, let me see if I can go ahead and get what T of T is. Let's see if I can build this in here real quick. T of T. Oh, cool. I think I have something from before that I can put. Okay. Sorry. Guys. Oh, are we ready? Let me see. T of T. So that would be, if I just do this directly, I'm just dividing this by this. What does that do again? Don't tell me it tells me what T of T is. What?
Unit.
Yes, it makes it unit. If I take any vector in the universe and divide by its length, it becomes a unit vector. Pointing in the direction of the original vector, correct?
Yes.
In general, why is that useful? Because it becomes a good building block for other things. It just maintains information about direction. It doesn't mess with the length in whatever else I'm doing. So this would be 4t divided by this. All the t's are going to cancel, yes?
Wait, wouldn't it be 4t over 8 over 17?
No. This is the answer to the integral.
Oh, okay.
T needs r prime divided by its length. Yes?
Is the unit vector going to be the same thing as the directional vector, how it's called in the book?
Yes. Let me make sure what the book calls a direction vector.
I imagine.
Oh, no. Okay, direction vector could be the v for a line, and that doesn't have to be unit in length.
Mm-hmm.
What I just said, I got to be really careful with what I say because I got to remember what the book terminology is. when I say direction vector, what I think to myself is something that merely contains direction information, which would be a unit. I think the book, in general, you could be more open about a direction vector just being the direction in which something's going to go. It doesn't have to be a unit. Does that make sense?
Yeah.
To me, it makes more sense to have a vector that purely has directional information.
But like for example, in the homework we have direction. We can.
Oh, direction cosines and such?
We can get direction vector of the, I guess, the curve, like the parametric curve.
Sure.
And for example, if it's like really curved, would the direction vector just look from A to B, like kind of point to the B, or would it be?
No. Yeah. So if I want to get here, the direction vector is always pointing the way that I'm moving.
Okay.
Yeah. So it's like again, real quick, guys, real quick. This is perfect. Can you guys? What do you need to make the equation of a line in any dimensional space? What two things do you need? In two space, in xy plane, I just need a point and a slope. Yes. The slope, that phrase doesn't make shit bit of sense in higher dimensions. So what two things do I need in any dimensional space to create a line going through that space?
Direction of magnitude?
Yeah, direction vector. So that's what we call V, the little V dude. So it'd be plus TV, yes? And then a
Magnitude.
point on the line. Yeah. So just like so the direction vector takes the place of the slope because it has to have information about all the different directions this thing could go in, yes? In 2D, I just need 2 bits of information, that's a ratio, B to A. Or delta Y, delta X, yes? You guys with me? And that's why I was able to make it a single ratio. In 3D, I can't make a single ratio because I have 3 components, yes? So we just made vectors. It has all that information in it. So I still need the same shit. I still need a way I'm going and a starting point. Yes, that's all I need in any space. It's just when I go up in space, I can't use a slope. The way I'm going is a vector. So they might reference the direction vector. It might not be a unit vector. Okay. So coming back to this, I'm going to lose my t in each one, right? Because I'm divided by t rad 17, so it'll be 4 over rad 17, sine over rad 17, and cosine over rad 17. This is even better than I remember. I think we made a mistake. No. You guys with me? Semi with me? So I really hope that some of the concepts behind these made sense. That's always a bonus. That's a big time bonus. It's like finding one extra cookie in there when you thought they were all gone. But as long as you're just able to crank out the math, that'll get you through. What is this vector's whole point?
T prime over the one.
No, what's its point? What's its meaning? What is it doing?
It's like the unit vector of the tangent unit vector. Something like
Is a unit normal?
It's a normal vector. Normal to the
Tangent vector?
tangent vector, so it's normal to the direction of motion. So just like, hopefully in 80, some of you guys had find the equation of the tangent line, and then part B was find the equation of the normal line. And that's just the line that's perpendicular, yes? So if I consider, everybody remind me, how many vectors do I need to define a plane? 2. 2 vectors define a plane, as long as the vectors are not parallel, yes? 2 vectors define a plane. T and N together define that plane where that osculating circle lives. Remember that shit? So it moves, it kind of tries to contain the instantaneous motion I'm having. So if I'm going up a little bit, then it's going to do this. The plane, the TN plane is going to go with me. It's kind of like the 3D analog to the 2D idea of tangent line. So it's roughly a tangent plane. Yes?
So, I think you went over this last time, but n can if I'm turning this way, n can do this, go this way, but it will flip if I turn this way.
Yeah, so N does contain information about which way your curve is going. Yes. Not only left and right, but up and down and so forth. Yes. Okay. We'll see. I'll show you the end result of this and how the TNB reference frame. I think I just got it. Okay. So how do I construct n of t?
The derivative of t over the.
Yeah. So what do I have to calculate next?
The derivative.
Yeah. So go ahead. So right there, I need the derivative of t divided by its length. So figure out the derivative of t. Let's see. What am I missing? Okay. I think that's it. Let's see. What did I do? Yeah, okay, that works. Yeah, that's fun. All right, I like it. Yeah, that's good. That's perfect. Oh, that's pretty good. I'm sorry. I'll shut up. All right, that's better. Okay. So, t prime should be pretty straightforward. Yes. What's t prime?
0
0.
cosine t
Cosine t over rad 17.
negative sine.
Negative sine t over rad 17. So anybody started on its length?
It's radical 1 over 17.
Yeah, so let's see. It'll okay, I'm gonna catch up to you. So it'll be the square 0 square of cosine over 17 plus the square negative sine, so plus the square of sine over 17. I'm squaring each piece, yes? We already know sine squared plus cosine squared is 1, so I end up with 1 over rad 17. Which, to be honest,
Wait, would it be radical 1 over 17, not 1 over rad 17?
what's the square root of 1?
1.
Yeah. Okay. So I'm sorry, there's another question? Yes.
Oh yeah, would those four formulas on the top right be provided on the exam?
What do you guys think? Should I?
Yes.
Should I give you guys this? Okay. I'm sorry, you might have come in after I said it.
Oh, sorry.
So I'll give you at least these. I might give you the other ones we talked about, yeah. Depending on the function they give. But you guys see how this function looked like it was going to be a lot of trouble. Yeah? But then some trig identities saved us. And now we're at this point, I mean, that's beautiful. Now this t prime vector has a constant length, which if we were in a class that was really analyzing these TNB reference frames, we would talk about what that means and so forth. I'm going to let you guys kind of think about what that might mean. It's obviously potentially significant, yes? If I ever see something come out as a constant, in this case the length of the rate of change of my unit tangent vector, that tells me something important about how this thing is moving. Okay, so maybe I'll have a bonus question about that. So I haven't constructed entity yet, have I?
No.
But entities, oh, and I forgot, I did want to say this. Guys, if I had a vector that was cosine t, comma sine t, r2, r squared, what is its length? 1. Do you see how t prime is basically 1 over rad 17 times 0 cosine negative sine? So of course the length is 1 over rad 17. Okay. Maybe. Does it always have to happen that way? No. I just gave us a really, really nice function. So how do I make n of t? I just take this divided by this, so I end up with something really, really beautiful.
0 cosine t negative sine t.
Yes, which we would not have guessed from the beginning. And then what is b? What's the vector b?
T cosine.
Yes, t cross n, and of course we have to be very careful. Some of you guys are sometimes mixing up the order. Cross product is not commutative, so you have to be really clear about what you're putting first. Some of you guys, okay, no matter what method you use, you have to make sure you put the correct parts first and second. I think most of us do the determinant way, the shortcut way. Some of us do the straight up determinant, and a couple of us do the A2, B3 minus. I have a little special place in my heart for you, because I don't have any room left over in my head, so to put you somewhere. Okay, let me stop for a minute. The math we've done is new to you this semester, but it's not new in terms of this class. All the math that went into doing this is old stuff. You guys agree? We know how to find the length of the vector. It's not really old, the derivative of a vector, but taking the derivative of functions is really old. So that's basically all that is. Yes, so, okay. I'm not trying to make you feel bad if you have trouble with this. I just want you to realize this is just repackaged stuff being used for a very specific purpose. So to find B, I have to do t cross n. So if I want to do it this way, I can do this. So I got to first put t. Here's t. 4 rad 17. Sine. I should have given myself more room. Dang it. Cosine. 4 rad 17. Sine rad 17. Okay.
What did you write after the N?
Oh, it's a little arrow, sorry.
Oh.
It's trying to be a little arrow, poor little guy. And then I want n, which we just did. 0, cosine, negative sine, 0, cosine. Okay. So it feels like this should come out decent. Crap. If you can't read what I'm writing, then just put t first and put n second. And now, yeah, all right. So what I get here for the i's,
4 rad 17 cosine minus cosine over rad 17 cosine.
I'm sure it just happened. So I get negative sine squared over rad 17, yes? And then this way I get minus cosine squared. Is that okay? Oops, sorry. Let me stop for a minute. Is that okay? And again, if you do it a different way, okay, do it that way. But for my i's, I get negative sine squared, right? Negative sine squared. Choo-choo-choo. And then I get minus cosine squared.
And that'll simplify to negative.
It will eventually, I know. Let's get there one step at a time. So.
Okay.
Yeah. Then for the j's, I get 0 minus negative, so plus 4 sine for square root of 17. That's J. Man, if I can ever write, everybody's going to celebrate. I do this so you guys know I'm aware. And then for my K's, I get 4 cosine over rad 17. And then I get 0 here. So if I want to put this, and this is B, so if I want to put this, so like you just said, if I take a negative 1 over rad 17 out, this is 1. So I get negative 1 over rad 17, 4 sine t over rad 17, and 4 cosine t over rad 17. That's B. So I mean, I think you guys might see that the problem I give you, if I give you a problem like this, will require some understanding of basic trig identities to simplify. I'm not sure what you're trying to, I'm trying to see what you're trying to see. Yeah, I'm trying to read it, just. So what is this vector's deal? So that plane we talked about earlier that contains the oscillating circle, this is the vector that is normal to it. I like it. So it together with the other two create this three-dimensional reference frame that kind of travels with me, and it rotates as I do weird shit. Yes? Okay, and then what's the little kappa dude?
It's the length of T prime over the.
Yeah, it's curvature, and I do this business to it. Yes? What was the length of T prime? That was nice.
1 over rad 17.
Yeah, 1 over rad 17 over the length of R prime.
Which is T rad 17.
Yeah, where'd it go? T rad 17. So that would be 1 over 17T, if I do my math correctly. Which is neat.
Well, because as time goes on, it will get less and less curvy. Like the curvature becomes a smaller value.
So what does that mean? As you let time go on, my space curve should
Become linear. Essentially.
straighten out a bit.
Yeah, it'll straight.
It never gets to 0,
No.
but it gets
It'll approach
smaller and
it.
smaller.
Yeah.
Perfect. Okay. Here. Right? I mean, so curvature 0 means that you've got a straight line. Yes? If the curvature is constant and non-zero, at least circular in that area. Yes? It doesn't always, it could be circled for a moment. Depends on what kind of weird functions you got. Curvature like this, you can reason out as I let my t get bigger, it approaches 0. 0 curvature means linear, so it becomes more and more linear. Okay. And part of that, I don't know if I want to get into this too much. Part of that's because this guy kind of dominates both of these guys. So the whole, anyway, we'll see. I'll graph it here in a minute. And then these would just be a bunch of plugging shit in, yes? So here. I think, that would just be plugging stuff in. Yes? Is that okay? We can all do that crap. I want to show you the picture of what's going on. I think I got this set. Here, you guys help me. Tell me if I got the function in here right. Yeah, that's the function, right? Yeah, okay. Don't worry about this other stuff. So, let me show you our little dude here. Come here. Get up here. No, not down. Alright. He doesn't look too exciting, but we should all thank him because that's why the math was so nice. I mean, I think you guys can see how it wouldn't take much of a function to make the math really get bad really quickly. Yes? Or not bad, but like not what we would hope for. So I have to kind of use a function that doesn't have a ton of stuff going on. But this does have a little bit going on. I mean, do you see how it's... Alright, let's see. When it starts, it looks like it's coming straight out, like along the x-axis, but then it starts to go this way. Let me see what I can do. Let me see. If I look at it straight on this way, it just looks like that. But I see how it's coming out of the xz plane. Right? And then it starts to come down. Yes? So can you imagine you're on this roller coaster and you come out and you start to go down and around. So you see how your reference frame would be moving like that? So let's see what this looks like. Okay, maybe. All right, I'm not sure what vantage point to give us here. Okay, here comes the TMB reference frame. Oh shit, it's so tiny. Poor little guy. All right, real quick. See, we come out of there going straight, basically. Right there it would be almost, I don't know if you guys can see, it would be perpendicular to, or parallel with our current reference frame, the XYZ. And then when I come out, I start to curve. I start to twist. You see how I immediately start to twist? I don't know if you guys can see that. So watch the reference frame. Watch what it does. I twist, and then I start going down. I couldn't remember how to get my I'm not sure why my B's not showing up. It's okay. Is it not showing up?
That's good, right?
It is.
All three of them.
You can have the blue one.
It's the red one.
Can I just not see? Oh, it's the red guy. Oh, it's okay. Okay, there we go.
It's going in the direction of the curve.
Yeah. Oh, my B is blue. Okay, there you go. There's the red one is what I'm losing. That's the tangential one, which makes sense. It's going relatively straight from the beginning. It has a little bit of a twist, but I think you guys would agree that compared to some of the other stuff I showed you, this is not turning much. Which again is why the math was really nice. Which is why the T is even harder to see because it's matching it pretty well. So it kind of blended in. We can see the other guy's easy. Okay, let me stop for a minute. And again, this is all in Desmos. I had kind of built this a while back, I think, and saved it. You can save shit on Desmos. So I just had to remember where the hell it was and put shit in here. So everything I did here, you guys could do. If you wanted to investigate how to work it. Okay. Is that okay? Again, if this was an aerospace engineering or like a trajectory for monitoring spacecraft or whatever, we would get a lot deeper into, well, what does it mean if the vector's length becomes this, and what does it mean if I notice that this derivative is 0? What does it mean? They would all have implications in terms of what's happening with whatever I'm tracking. But we're not in that class. So we're in this class. So I'm mostly concerned about, can you do the math? Yes. Okay. So is everybody cool with that? I wanted to do at least one concrete example of all the stuff we did last time. Okay. And also I didn't really put one on the test, and I figured I could just do it separate. So the rest of today, if there's more questions on what we just did, feel free. I don't know how to really get you guys to understand this. This is our first practice review day. This is our first review day. If anybody's had me for class before, you know that I bring very little. It's all dependent on what you guys want to ask. So today's the day to just ask anything. You got a problem in homework that you're hating, that also seems to hate you. If you have a problem from the practice test, from the quizzes, a general question about what the shit is this again, whatever, we can do several problems. It's completely up to you guys though. So we'll see how it goes. If nobody's asking questions, you've got the floor. You can ask whatever the hell you want to. Math related better, Calc 3 related even better. Or is everybody ready? Are we all ready? Should I have brought the test? Did I brought? Oh man. Huh?
Just a question. So it's just on 12 the 12 material, chapter 12 material?
No, what's this up through? 12:1 through 13:3.
13:3.
Okay.
Is 13:4 going to be on the next test or no?
It's extra credit. I am going to talk about 13:4 a little bit after the day after the test.
Yeah.
Just because. And I'll make that due the day of the final. So on the final, I'll have some bonus questions on the final. So I might have one from section 13:4, just to further reward anybody who wants to do that section. Every test I give 3 bonus questions, by the way.
Yeah.
So every test you could get up to 106. Which makes that A+ even easier to get. So. Or you could have 6 points that will help you if you miss something else. Yes. Okay. What's up? Yes.
Oh, no, I was telling her to.
Okay. She disagrees. Yes.
So for the osculating circle is a concept. That circle is essentially dependent upon the curvature at whatever given point it is.
Yep.
And that circle, the way you tell what it is the radius of that circle is 1 over the curvature.
Beautiful. And the curvature for us was what again? What was the curvature?
17.
Yeah, 1 over 17t, yes? So, guys, I don't know if you remember, I can maybe pull this up again, but I showed you the oscillating circle. And when things got more straight, it got huge. Yes? And when things got perfectly straight, that's basically infinite radius, it's just a line there. So what's interesting is when it's tighter curvature, the circle's smaller, because that would mean the curvature would be smaller then, relative to the amount of room that it's working with. Does that make sense?
Yeah, I mean, circle in this problem specifically would start out being small and eventually grow to
Yes,
infinity.
because its radius is equal to 1 over k, 1 over kappa, so that would be 17t. So at 0, it's got 0 radius. Yes? Now, can somebody point out any math in the problem we just did that shows why I said t greater than 0? Now, as I say that, I'm like,
Yeah, it's not about
yeah, I think somewhere, where was it?
Yeah.
Wasn't there somewhere with a t in the bottom?
The very top, number 1. Where t is greater than 0.
No. I was trying to remember, trying to say why did I say that? But I guess there's not really a reason. I thought there was a t on the bottom somewhere, but as I said it. Oh, well, I mean the curvature. Oh, you guys are like, you're talking to yourself, John. The curvature at 0 would be. Well, would be no. Curvature at 0 would be undefined. Would approach infinity as I approach 0. I don't know why I thought there was a t on the bottom somewhere, but yeah, I could have said t greater than or equal to 0, but maybe this is why I say greater than 0. Trying to remember. All right. So yeah, at 0, the curvature would be infinite. The radius would be 0. Yes.
Can we do number 2 from practice test?
Oh, before, real quick, one last thing about this. Can I go? No, because let me change this so I can go negative t. Ooh. All right, sorry. Stop. Oh no, I got this in the wrong place. Jeff, where's my t stuff at? Here it is. Do you see what happens? I'm just kind of following the line back out. So it's kind of like hitting the wall and bouncing back. That's kind of why it makes sense the curvature goes insane at that point, because it's an immediate bounce back. I just follow the same track back out. Okay. What's the question?
Number 2.
2 on the practice
I
test.
understand it's about projections.
Oh yeah, okay. There's 2 ways to do this problem. And I'm always curious which ways people do it. I didn't say you had to do that a certain way. I want the component of u parallel to v. Now that one, there's a specific thing you can do. Real quick, what's the projection of u on v? Yeah, okay, the equation's great. It's a vector, correct? I'm sorry. I appreciate that. The component of u parallel to v is scalar. In fact, it's just the first part of the projection formula. Because, like you're saying, projection of, where'd it go? U on v would be u dot v divided by the length of v squared on v times v, the vector v, so you're pointing in that same direction. So if you just take times the vector v out, that's the component of it. So one way to do this problem is to find the angle between those two, and then you can just kind of draw it and do right angle trigonometry. Because I'm just asking you to take something and break it up into its x and y parts, based on v kind of tells me where my x-axis is. Yes?
Are we gonna get that equation on the exam?
On the day of the quiz, I'm pretty sure I told you guys I would give it to you for the quiz, but on the test you have me know. Yeah, okay. You're welcome. So the way to remember is if I ask you projection of m, let me say it correctly, b on m, what would that equation be? M dot b
over the change of m squared.
the length of m squared. Oh, I'm doing where are my 284 people at? It's alright, let me make this one big.
Dot
times m, not dot.
Yeah.
Because what kind of thing is this? Is it vector, scalar, line, plane, rhombus? Scalar. Yeah, in fact, that part is the component of B along n. So if I do projection of something on something else, that's why the m is on the bottom. That's why I multiply by n, because I've got to be in the direction of n. I've got to be on the m vector, so I have to multiply by it, so I'm lying on it. How often did this vector show up? Once. So there's a lot of different ways you can kind of get this in your head. If on a test you need a kick in the right direction, just come up here, right? Come up to see me and say, I think this is it, and very often it's correct, you just aren't sure. Just show me what you think it is. And I'll tell you what part's not quite right if something's not quite right. Are you with me? I'm the only one you could do that with, so you might as well do it if you need to. So this question here, did anyone try this question out yet?
Yeah.
How did you do it? Did you do it using,
For the parallel part, I just found the projection and then divided, and I just found the I was only able to find the projection of it.
sure.
And then for the orthogonal part, I just did u minus the projection.
Oh yeah, so there's a homework problem that talks about, and this I'm not going to hold you to, but if you remember, your homework sometimes establishes things like that. There's a homework problem where it said, I think it was B minus
B minus
projection of
A.
B on A.
Yeah, something like that.
Yeah. And that becomes the orthogonal. Yeah. So you could do it the way that you learned in the homework. I like it.
So the parallel part would be the projection answer, and then the orthogonal is just the u minus the projection.
Yeah, and if you want to think about it as right triangle trigonometry, you think of u as your given, you get the angle between u and v, and then it's just right angle trigonometry. To find the length of this side. I think on the practice answer key, I think I did it the way you were talking about. Yeah, oh, I did it both ways. Look at me go. Yeah, okay, I like it. I'll give you that key in a bit. So there's at least two ways to do number two. Hopefully one of them makes sense.
What about the component of u orthogonal to v?
So we gave a couple ways to do it. One was from the homework, where you can take the vector minus the projection to get the orthogonal component. So let's see. So you get this piece. I just have to do this piece.
Oh, you don't need a dot v?
Two things. This
Or-
can't be dot b because that's a
Or I
number.
meant you don't need a multiply?
Because I just want the component, not the vector.
Oh.
I don't want the vector parallel of piece of u. I want the component. I don't want the projection. So that's why I can use right triangle trigonometry, because I just care about the lengths of things.
So the answer is two scalars.
Two scalars. Yes. And I thought for sure that's how I started the discussion about projection. Let me see. No. Where'd you go? Here it is. Yeah. Woo-hoo! So scalar projection, that's the component. The component of B along A, get out here, is this piece.
So you just wanted the a dot b over a.
Yeah. So this is not squared, because the thing with the projection formula, the reason that's an a squared on the bottom is because we moved that length over, we had to make a unit vector for a, so that I didn't mess up my length of what I wanted. So, yeah, this should be not squared. There we go. So you could do the projection and then figure out, well, let's see. I guess you could backwards do it.
I mean, projection is.
The other way to do this, here, let me do
What's
this.
the length of the projection?
Let me give you this, and we'll talk about the other way to do this. This answer key, by the way, has got 2 pages to it. And it's my writing, so good luck. Anytime. Oh, I think you take the length.
Oh, I just found the right. Got it.
So the component part should be here.
Got it.
So if you want to square it, choose something else.
Anytime.
You wanna go?
Is it? Yes, thank you so much.
So 7/5.
Appreciate it. Thank you.
No problem. Alright. Did I miss anybody? Alright. Oh, man, now I'm curious what Pastor Jeff did. There he goes. Whoa. So you can do this very directly. And the way I get I didn't do it the other way, that's right. I just did it using basically Pythagorean theorem. And then this is just getting the angle first and then breaking the rad 29 length into its components. I think I did that. It should come out the same values that you get for these two things. So Zach, if you take your work you did and, if you find the projection, it's not going to be the right length because that's only divided by the length of E once. So you have to find the length and then multiply what you get by the length of V. To work backwards to get the component.
So if the length of V is like 5, I just multiply that by 5.
Yeah.
Okay.
Because you like divided by V twice. So the projection, yeah. But if I were you, if you're just trying to take a vector I give you and break it down into its components, where the x direction is based on the other vector I give you. Alright, so this is vector u, this is vector v. And now with the orthogonal, the component of this that lies in this direction, this is effectively my x-axis. Then I could do right triangle trigonometry. And of course, triangles, I don't have to have them in a coordinate system to be able to do basic sine and cosine stuff with them, right? So that's that second way to do it, is a little bit of Calc 3 to start with, and then trig. Yeah. So let's see what I can do here. I can't remember if I did it to double check, but don't, yeah, okay. I think yes, I did. I thought I wrote relatively well for myself. Yeah,
Yeah, it's pretty good.
yeah. You don't have to say that. It still sucks, but for me, it's pretty good. Okay. Please, dear God, this is the first time some of you guys have ever had me for class. So this is the first time you're ever seeing a practice test. If you didn't try the practice test out, do not do this. Yeah. Mm-hmm.
Yeah, that's totally the answer.
I would have done that. Yeah. Because then you're building up false confidence. It's easier to agree with me than it is to do. So if you didn't do the practice test, do not look at the key at all. The only time you look at this is if you actually did something. Does that make sense? Trust me. Also, don't do the practice test problems more than twice. If you're doing a problem over and over and over again, you're getting to know that problem really well, and I'm not going to give you that problem. So if there's a problem on the test that's giving you a lot of trouble, find an example like it in the book. Or, you got the ebook if you got the Web of Science business. Yes? You guys with me? Okay. People do that. They'll say, I looked at your practice test for 8 hours and I did them over and over. And I'm like, no, don't do that. Don't do it. So, if you've tried to practice this out, you can check against this. Let me know if you think, if you want to know why something's different. I am human. I am completely open to the possibility that I made mistakes. Because I created this myself. I didn't take it out of anywhere. So I'm averaging about a 97 on my entry keys, which I think is pretty good. But students don't understand why it's not 100. It's because, I'm a human. Yes.
I have a question about one page. I was just wondering if I did it right.
Oh.
Yeah. So
Yeah.
that's it.
Yeah.
'Cause
What was it? 1H. Didn't you know angles and such at that
It's
point?
different, that's what I was wondering. Yeah, two sides.
So let's see. Yeah, 210 comes from this.
Oh, here we go.
Angle between U and B is 9. Yes. But isn't the angle between U and V 90?
It doesn't. Because there's no angle given.
Let's see, why did I think that?
Because wouldn't it just be the cross
Here.
product and it's.
Oh, yeah. Part C, didn't you get 0?
Oh, yeah, there it is.
So the angle's 90.
Oh, okay, so that's.
Which means the shortcut for area parallelogram is shortcut for the length of the cross product is the magnitudes of the vectors multiplied times sine theta.
Okay.
So something either, I am open to my numbers being a little off, but let's see.
I just found the area that failed. I just did the cross product.
Yeah, yeah.
and I found the length.
So
Is that also what we're
it should agree with what I got if they're both.
Yeah, it's not.
Alex,
Yeah,
yeah.
wrong. So
-3. Oh, right here.
minus 2.
-2, yeah.
Yeah, there we go.
Well, I mean, what's 4 plus 25 plus 9? Yeah, right. 4 plus 25 plus 9.
There we go.
Hey, there you go. So you only took a point off. I mean, so guys, I think I told you this before. If you're in the middle of a lot of crazy ass work, which if you're in 281, you always are, and you say like 8 plus 3 is 10, which is neat, right? my mathematics, my osculating circle, hello. I might not even take a point off, as long as, I might take a point off at most, you know what I mean? So your answer's gonna be wrong, but if everything after that is correct, I'm not gonna take much off at all, because, dude, I can relate to that shit so much. I've done that so many times. 8 plus 2 is 16. Yeah, Jeff. You know, I mean, it's so fun to do that in front of a whole room full of people. It's the best thing.
Isn't the length of you the 35?
Length of view,
Because it's
35. Why did it say 29? Oh, this number 2.
Oh, that's a different one. I was like,
See, I was like, here I go.
I was like, but for my number 2, so that's the parallel.
Oh, did the numbers come out? Yeah.
Yeah, I just added wrong. And then, so this is my component. So
Yes.
component of phase 5, and then you just phase 7. And then,
Okay, good. So you got the same thing.
and then, so that's the parallel, and then.
Oh, and this you can do the same
Yeah, so I
thing.
did the U minus the projection, which
Yeah.
I already
Now
solved.
that math is a little
And
trickier
then
how
I
it
would just
goes backwards.
And then did I just did the orthogonal U, and I got 5 with that.
Yeah, see that gets a little tricky because
You
I'd have to sit down and think about how that, what math would be required to get what you get back to what I'm really asking for.
Okay, so
Because you're getting a vector that points in the direction that it needs to, but it's not the right one.
because I found the length, and then you said times it by the length of V.
Things get really tricky when you're doing the vector minus projection.
Because if you do it by that, you're gonna be, because I got 5 over, or 5 times. What is the?
What I-
2 root 178.
Yeah, you can check it out, see if it comes out the same. Yeah, don't hyper focus on any specific.
26. So this one's 26. And that one's 26.
That's nice.
And then
Yeah, really.
yeah, that's.
And then I'll help you out with this later. You don't have to do it that way, but it will help you. What's up?
That's the that's your answer. But
You want to stick to that?
yeah. So to find this one, you did use
29
so you
parallel.
oh parallel. So that's 7.
7 is squared.
Oh, you just
And then I subtract that. I might have done that wrong in my head. I think I did in my head.
oh, so this would be a subtraction.
No.
Oh,
That's adding, and then I subtract it to solve for it.
Oh, to solve for it. Okay. And then gotcha.
Boy, thank you. Let me see, I think Gianna's out. Is Ryan here, Daniel? Well, oh. Jake Hernandez? Or Christopher Quill? Jomaine? Jomaine?
Julian. Julian. Julian.
Yep. Cool. And as you see, several people are left already because they're ready.
No, we're not ready. They're gonna be a question. It's a non-study so now we go.
Is there gonna be like a question?
Good lord. a little obscure, we talked about it, its radius is 1 over the curvature at a point.
Right, so we
But I'm
have
not gonna ask, I mean, that would be a real detail that we haven't really looked for long enough. Maybe ask that. So, guys, quick opinion question for you guys. Besides the 13-3 equation, do you think I should give you anything else? I'll give you the answers to my other test.
That would be great.
Okay. 7. Square root of 31. Sine of the inverse tangent. What? Yes? No, anything? Do you guys, is there, you guys really aren't used to democracy. By the way, I probably get shoot down whatever you say, but I'm open to the possibility that there's something that makes sense. Alright, so no? Okay. Oh, I like this, alright. Democracy in action. So I'm sorry, yeah, what's up? Did you have a,
I'm trying to understand the second one, practices number 2. I
uh,
don't understand how to do the component cardinal to be without dot or cross one.
oh. So, again, the whole idea of this is more, what I really wanted to happen here was for people to realize this is just a trick question. Because we know how to get the angle between these, and therefore I can break this up into components that lie in this direction.
So how would you do that? Do you just multiply by sine or cosine?
If I know the length of this, and then the angle between the two vectors,
Oh,
I can just,
okay.
yeah. You see what I mean? That was the second way I did it. I did it the first way because I thought maybe people would try that way first, because I think they're supposed to use all the formulas. But again, I keep a problem like that, if you graph it, if you show yourself what's going on,
Yeah.
you might realize, oh, it's just a trick question. If I don't say you have to use a certain formula, yeah,
Okay, so the idea is, we find the projection of u and that gives us a right here, right? When we make that orthogonal, that gives us that 90 degrees.
yeah. It's kind of like, all right, guys. Does everybody agree with me that the x-axis goes forever? So if I ask you to break up the components of this vector, not drawn to scale, but I kind of drew that in automatically, because the components of this would be its true shadow, and then the other piece, right? So Pythagorean theorem can come into play, trig can come into play, right? So the way I did it on the first part was I found the components by a formula, the formula that came before projection, and then I did Pythagorean theorem to get the other side. It literally is just your two answers better square and add to be the square of the original thing's length, because it's the components of it. They have to together make it. Yes. Does that make sense? All
It makes a lot of sense.
Cool. I'm okay even if it just makes a little bit. Yeah.
So I was doing the math right here, so I have the 29 is equal to the square of well, if you do.
Oh yeah, this
I did it.
I should have done it in the calculator. I remember doing this in my head.
Because I did it in the calculator and I got to that 27.
Oh, you got it.
So it's the same thing. It's just so the other formula that it's the.
No, this will work.
Yeah,
I think I just did this in my head wrong.
Yeah, because the other formula is that to find that u. To find that length of u, you just do the u minus the projection.
Yeah, so guys, right here, here's a great illustration of why I sometimes get like an A minus. This I did in my head, which was a bad choice. So if you got to do 29 minus 49 over 25,
which is 27.
yeah, so then I got to multiply this by 25 and subtract. Yeah?
Yeah.
And I remember what I tried to do, and I have no idea why I didn't double check it. Probably because I had zero time. I swear to God, this work. Anyway, you guys agree. I took like one break this weekend, but if you just do this, I don't think you quite get what I got because I did this in my head wrong. But this idea is correct. Whatever this would be.
But would it, and then the
25 times 28 is 700.
676 over
700. So then one more 725 minus 49 is 676
over 25.
over 25. Okay.
Square root.
Somewhere in there, I did something way too nifty in my head.
So that
97%.
Yeah,
so that
that's
other,
pretty good for government work.
So that other way I did it also works because
No, yeah, totally.
yeah,
Which is great. I'm glad you did it that way, so you can double check it against what I did. And I made a silly mistake right there. More than likely.
so yeah, so it's just like the other way is just
I think my plan was to do it the other way and double check against what I got. I just didn't have time.
yeah, because it's just the length of view minus the projection.
The length of view.
Yeah, because that's because
Oh, the length of
yeah, like
view minus projection. Okay.
is that component
Is the component.
is the
okay,
component
okay.
that they're looking for.
Okay. I just hadn't done it that way in a long time. I had no idea if that would actually get there. I just always kind of revert back to trig. Because if you have two vectors, even if they live officially in 87-dimensional space, they still are in a plane.
Yeah.
All our plane trigonometry stuff still would apply. It's kind of crazy.
Because the only thing we've learned so far that can't translate is cross products.
Cross product, yeah. Well, like I said, that has a analog. Maybe I'll, yeah. I don't want to focus too much on that. I mean, everything we're doing in here has
Yeah.
potential other analogs. I mean, you have matrices that. Did we talk about matrices? No, we just talked about vectors. I'm not thinking about linear.
Yeah, that's the other.
I mean, later in math, you learn you could have a matrix made of matrices.
Makes sense.
And those we call tensors, and that's like the next level up,
Yeah. You go from a vector, which is one line, and a matrix that's
which is a
two
collection of
dimensions.
those.
Yeah, which is 2 dimensions.
And then you get this thing called a tensor, which is a collection of a bunch of matrices.
Yeah.
Yeah. And of course, you could just continue that until you go and say, yes.
Explain what the parts of numbers
Oh! To be really honest, number 6 is a purely mathematical exercise. I mean, yeah, and that sounds weird to say, we're in a math class, but like number 6, this has potential physical interpretation. This has a potential physical interpretation. It's kind of like if somebody changed the amount of time that I'm kind of recording this thing moving, if I wanted it to be in terms of e to the 3t instead, or something. But I'm not asking for a geometrical interpretation. Yeah. B is just, do you remember how to take the derivative of a vector with a function, right? So that's that. What rule would part B require? Chain. Yeah. Because it's a function inside of a function. Yes. Part C is just, if you can differentiate a space curve, you should be able to integrate one. And part D is just, okay, if you can differentiate a space curve, you can differentiate that derivative and differentiate that derivative. I mean, it's just a reminder that every time we do calculus to a space curve, we get another space curve. That is its own thing. It exists, so I can do shit to it. And every time I do it, I get another thing that exists, and I can do more stuff to that. Does that make sense? Which is kind of like the analogy of in Calc 1, he took a derivative, and we tried to make sure everybody understood that derivative is its own function. It exists. It's its own thing. It could have a derivative that describes how quickly it changes. That happens to be the second derivative of the original, but it gets its own derivative. It's its own little function. Okay. Poor little guy.
It's crazy how math involved. You think, oh, Calc 1 is so, when you go into Calc 1, it can be like really kind of confusing to start with. And now we're here, and it's just like, that stuff was so easy.
Just wait till you get to class where this stuff is so easy. Yeah. Yeah. Yes.
I have a question on the whole problem.
Yeah.
I just want to know if I'm correct on the way. So this, it's one thing to find the water intersection with these two points.
Yeah.
Just leave this cross this with the and then it's on water.
So if you do, so you got your two normal vectors,
Yeah.
and if you cross those, so everything that's perpendicular to this is in this way.
Yeah.
Everything's perpendicular to this is in this way.
Yeah.
So if you cross those, you're automatically in both planes. Is that your thought process?
Yeah.
Because if you cross them, you get something perpendicular to this, which means you're in that plane. And you get something perpendicular to this, so you're in that plane. I didn't know what your thought process was, or if you saw like an example somewhere. I
I'm
wanted to
just
make
trying
sure.
to think through it and use like my notes.
Okay.
I don't really.
No, it sounds right, yeah.
So that and then just instead of like any other equations.
So what they give you is line of intersection. Now you just need a point that's on the line.
So there's either of these.
What do you mean? Those aren't points, those are vectors. So
just
just
find
need
like
a
a
point
ring.
that's on the line, yeah.
Just any other point of work.
It's gotta be on, a point that's on both points. To be on the line.
Yeah.
Does that make sense? I mean,
So I was
now you
like
need something
setting
that.
like one of the variables to like 0 or 1,
Oh, sure.
and I would just find.
You can, yeah, that'll work. You need any point that would be on the line, which means any point that would be in both planes.
Yeah.
Does that make sense?
Yeah.
Okay. So it sounds like you got a nice way to do it. Yeah.
This all you want to cross that out.
Oh, yeah. Always give me exact answers. Unless I specifically say round it to something, right? Yeah.
So that's good, and then here, you just help me out, please, I'm ready to issue, there's certain magnitude, right?
Oh, no, you can pick right up where the last good place, so just rewrite it with the appropriate signs. Yeah.
Just rewrite it.
I'm not gonna make you redo it. Yeah.
Yeah, I just put a little negative, that's all.
Just make sure it's really evident to me what's happening, what changed.
Yeah, I put a little note.
Okay. That's fine. Yep.
Bro. Good.
So you did, I'm not sure what you did. Oh, okay. You didn't get anywhere with this. So your thought process is not wrong, it's just so much more than you need. So, if I want a vector parallel to A cross B, what is A cross B? Well, now you know it's. Yeah, so if I want a vector parallel to that, I can just double it. A vector parallel just has to be in the same direction as it. Right? Now, I want specifically the vector parallel to that as a circle. So I should first take the vector I'm talking about, A plus B, and then I should do the I plus length. That'll make it a unit vector. Then multiply by whatever language you want. So your thought process wasn't necessarily wrong, which is so much more than you need. Yeah?
Was it possible again?
Huh?
It's possible to solve it.
It's possible. Yeah, that's always one answer is yes, possible. I don't know who would want to.
Symmetric.
Oh, that was the like x plus a over 7 equals. So when we go from parametric and we solve for t and we make them all equal,
Oh.
that's symmetric form.
Oh.
So there's a shortcut to symmetric form in terms of what goes on the
Where
bottom.
it becomes it's like a plane.
So it's like x minus x naught over a equals y minus y naught over b equals z minus z naught over c.
Right. And also the area of the parallelogram, that's the length of the cross.
Yes.
Hey, D. this
What is the length you
this is
want?
where we
for,
do the
uh,
homework and the test correction.
I mean, the formula. So it's only top five, which is
I usually do it
length
on
of u,
so I
length
wouldn't
of
know
v,
for
cosine theta.
Can you do the test correction?
The length of the cross product is
I
length of u,
I've not had
length
to
of
do
v,
test corrections,
sine theta.
mainly
Don't
because
you know the length of u?
I get everything right on the
Don't
first
you know the
list and I
length of
completely miss the
Don't
second.
you know theta? You do, because
Like, I was not here on class.
Oh, you missed the second quiz.
Yeah, so I got no material there. But, I mean, you could always just,
When we corrected it, you just wanted to do everything else,
Just the parts you lost points on. And if it's a long ass problem and you just made a mistake in like the second to last problem, you just pick it up. You don't have to rewrite.
Quiz
Good.
one,
Oh, thank you.
the question three.
should have it.
Yeah. Oh. Who? Oh, Jermaine.
He was here and he
A little sloppy.
and I let him know, like call him.
So I missed him. Shoot. Okay.
Thank you.
That was a neat space curve you just made. I like that.
Nice. It's better when they don't just
Plummet.
or just go boring.
I wanted to see.
Let me know if you have any questions about them.
Thank you so much.
Shoot. Yeah, watch this, guys. So here's that space curve, yes? But if I look at it straight down the x-axis, do you see how it curves around the x-axis? Isn't that kind of cool? No? Screw you, Jeff?
It's neat.
I wish I could make, let me see. All right, I'll mess with that. I need to make the TNB reference ring bigger so I can follow it. Get the multipliers in the right place. Aha. There we go. Well, it's a little much. All right. I'll let it go. Does anybody, I should have asked this when people were here. Have you guys tried out the tutors in the math science thing? Anybody? Yes? Are they useful? Are they helpful?
Yeah.
Mostly?
Mm-hmm.
Okay. And again, what's difficult for the students up there is they only recently took 281, they haven't taken much beyond it. So it's really weird to be tutoring something you haven't messed with a lot. Does it make any sense? Like when they tutor statistics, it's really hard for them because most of them haven't done another stats course. So they haven't played with those ideas in broader ways. So it's really hard to be a tutor when you've only seen it the same way the students currently. Does that make sense?
Yeah.
So I'm always curious how they're doing with the 281 stuff.
I mean, that checks out. It's like if a Calc 1 student that just finished Calc 1 was tutoring Calc 1.
Yeah.
You would know how to look at it differently like
Yes.
we do in this class.
Yes. You get a broader explanatory ability if you know where it's going eventually. Yeah.
Also just have more time to work with material.
Yeah, you get
Too.
Yeah. It's just living with it longer. Yeah. So I feel for him.
The thing that's nice with math and where it actually helps with psychology is that because math are always built on stuff, we're always using the older math, means that you're constantly being reminded of said older math.
which will just continuously reinforce it,
Yes.
because it's just spaced repetition.
Yes. That's it. That's what we call marinating in math.
On number 3, the angle was like greater than 90
Oh,
degrees.
sure.
So for the should the angle be, is it okay if it's like 100?
Well, all right.
Should
So
it
there's a
be less
bit
than
of disagreement about. All right, if it's more than 180, that's when you would kind of like turn it back on itself. So if I have two vectors that are like this angle is, if I change it, it's not the new angle is not measuring anything. It's measuring something in the triangle. So definitely gonna have the angle between two vectors bigger than 90. If it gets to be bigger than 180, that's when you would kind of like convert it back over. So you kind of like always stay internal to the angle. Does that make sense?
Yeah.
Okay. Yeah, because I think somebody did that, 90 minus or whatever, something like that. Oh, but yeah. It's good to be able, it's fine to be able to use as an angle. Gotcha. It's a very exciting video I'm taking.